Once we mathematically prove an integral exists, we have to determine the exact rules that govern how we can manipulate it. This defines the Riemann-Stieltjes integral. The true area under a curve is where the upper and lower sums converge across all possible partitions. But visual intuition hits a wall here. With infinite continuous systems, drawing rectangles is insufficient. We need strict algebraic rules. Can we treat these continuous integrals with the same predictable, finite algebra used for basic addition and subtraction? We can. To do so, we must prove that the integral acts as a linear, order-preserving operator, using only the logic of finite partitions. Mastering these operator properties provides the formal structure required for the rigorous proofs of advanced mathematical analysis. Every major theorem in analysis relies on these foundational rules to securely bound, estimate, and solve for the unknown. Looking directly at the text of Theorem 6.12, Section A establishes the formal rule for linearity. The mathematical claim states that the integral of two added functions is equal to the sum of their individual integrals. If we plot this on a graph, two distinct curves, f1 and f2, combine to form a single higher curve. At the partition level, the combined upper sum block is equal to stacking the individual blocks of f1 and f2. In Rudin's text, the proof works because this relationship holds true for the supremum and infimum across every possible discrete partition we could draw. Scalar multiplication behaves similarly. Scaling a function's height algebraically scales the resulting integral's value by that exact same constant, c. Linearity serves as a primary tool for simplification, allowing analysts to break complex continuous functions into manageable additive parts. Shifting focus from addition to comparison, Section B of the theorem introduces monotonicity. That states that integrals preserve the order of functions. The geometric translation is that if one curve is situated entirely lower than another, its total integrated area must be smaller. This leads to Theorem 6.12d, which uses monotonicity to build a rigid ceiling over an integral. In this inequality, m represents the absolute maximum value the function reaches on the given interval. Graphically, m forms a bounding box. Because the function never exceeds m, the total area of the curve can never exceed this rectangle. The mechanism behind this is rooted in partitions. Every individual term in the Riemann-Stieltjes sum is strictly bounded by m multiplied by the change in the interval, delta alpha. Summing those bounded partition blocks algebraically guarantees the total integral is less than the area of the bounding box. This guarantee means we do not need to calculate the exact integral to determine its maximum possible size. Monotonicity grants the power to definitively cap the size of unknown or uncomputable mathematical systems. Next, Section C defines the precise rules for slicing an integration interval into distinct subsections along the x-axis. Visually, dropping a straight vertical slice through a shape divides its total area into two smaller areas. However, an analytical complication arises if a partition block steps across point C and overlaps the boundary. To fix this, the proof forces the operations to only consider partitions that explicitly contain point C as a node. This property allows for piecewise analysis, letting mathematicians isolate and recombine specific regions of complex functions. These properties build towards Theorem 6.13, known as the continuous triangle inequality. It is one of the most frequently utilized tools in mathematical analysis. Standard integrals allow positive area above the axis and negative area below to cancel out, masking true magnitude. By applying an absolute value before integrating, the negative dips snap upwards, forcing the accumulation of all area. Total magnitude is revealed. How do we formally prove this inequality using partition rules without relying on a drawing? Rudin approaches the proof by defining a specific constant, c, and restricting its value to either 1 or -1. He chooses c so that the value of c times the integral of f results in a mathematically positive number. Because c is a constant, we can move it inside the integral, invoking the linearity rule we established in Theorem 6.12a. Once inside, c times f must be less than or equal to the absolute value of f. We can then invoke the monotonicity rule from 6.12b. This elegant sequence completes the formal proof, permanently linking the continuous behavior of absolute values directly to discrete algebraic comparison. The continuous triangle inequality ensures that magnitudes can always be bounded upward, which is required for convergence proofs. Finally, definition 6.14 examines a practical application of the Stieltjes variable of integration, alpha. The unit step function remains at 0 until it immediately jumps to 1. Using this as our integrator means the change in alpha is 0 everywhere except the jump, causing area to accumulate only at a single point. This behavior mimics a Dirac delta, effectively turning a continuous integral into a tool for discrete evaluation. The Riemann-Stieltjes integral bridges these two spaces, using the same operator rules to handle both continuous areas and isolated data points. Moving from pure theory to the realm of applied mathematics clearly shows the immense real-world significance of these foundational properties. In differential equations, these inequalities are used to bound error terms. In probability theory, these same rules ensure that expected values are mathematically guaranteed. This establishes our analytical framework. Linearity allows us to manipulate the system, monotonicity allows for comparison, and bounding enforces strict mathematical limits. By proving these properties through the logic of partitions, we establish the integral as a fundamental instrument for exact mathematical reasoning. For structured explanations of rigorous mathematical texts, including every theorem and proof trick, like and subscribe to continue your journey into higher analysis.